Welcome, Dr. Pollack, to the podcast.
Oh, I'm delighted to be with you. Absolutely.
It's an honor to have you on.
Well, thank you.
Well, your CV is quite impressive.
Well, there are a bunch of crazy people out there, I suppose, who like to bestow honors, and they're looking for people, and they must have selected me from the telephone book or something.
Well, for those that don't know you, what do you consider is important to know about yourself?
My name, where I live, what I enjoy for dessert.
Well, what?
I'm not sure. Well, so we've seriously, we've been studying water, and we found how should I say, information, facts that had been barely known. The idea that water has not 3 phases that we learn about, but 4 phases. And we discovered it, maybe 15 years ago or something like that, maybe even a couple of years more, and we've been studying it ever since. And it has a huge implication anywhere there's water, because the 4th phase is, it's not a laboratory curiosity, that it exists under strange conditions that you might have in a laboratory. It's there all the time, and it's everywhere, and it fills our bodies. So, contrary to what the textbook says about water inside our body, the textbook says it's plain old liquid water, the same as this stuff that I'm drinking, but it's not. It's actually 4th phase water, and the way you can tell that it's not liquid water is very simple. You take a sharp knife, and you cut yourself. Now, I know you don't write that, but you can do it anyway. Now, if your body were filled with liquid water, the water would come pouring out when you cut yourself, just like a breached water pipe. Crack in the water pipe, and you have tremendous flood all over. But that doesn't happen in your body. So it's not exactly liquid water. And we found this 4th phase is a gel-like. It's viscous, and it sticks to the solids inside your cell. So it's very different from liquid water. So when you ask what should people know about me or about the work that we've done, I think that's it. That the water inside our body, and also all over, not just inside our body, but outside our body too. There's a lot of this stuff. As I said, it's not just a rare laboratory curiosity. It's everywhere. And in fact, people or scientists in the past had noticed it, and they characterized it in a way that I believe is different from what we found. But essentially, it's similar. And people have been talking about a type of water in which the molecules are organized. It's kind of like a crystal. In liquid water, they're not organized. The water molecules are bouncing around furiously, many times per femtosecond. Really, really fast, and they're randomly oriented with respect to one another. But this is different. This is a phase in which the molecules are actually ordered. And early on, 30, 40 years ago, some well-known scientists were talking about biological water being ordered in some way, and they thought of it a bit differently from what we found. They thought that the molecules were their individual water molecules stacked on one another, kind of like soldiers at attention. And we found that it was not like that. It was different. And if you ask me, I can tell you. But the main point, excuse me, the main point is that the water that's, excuse me,
Bless you.
yeah. The main point is that the water is different from liquid water, and obviously it's not solid water or ice, and it's not water vapor. It's different. And the people who were talking about were really interesting, if not distinguished people. The primary one who spent pretty much all his life in the past couple of years ago is a guy named Gerald H. And Gerald H came from China, as you might guess from his name. And he came as a member of the first cohort of Chinese young scientists to come to this country. It was 1948, after World War II. And the Chinese government looked all over China to pick the three most promising scientists, and he apparently was one of them. They chose a physicist, a chemist, and a biologist. He was a biologist. The chemist won a Nobel Prize. The physicist won a Nobel Prize. And Gilbert Ning did not win a Nobel Prize, although many people think that he deserved at least 2 Nobel Prizes, but he was controversial. The idea that the water inside our cells was something different from what we'd known about. The controversial, to put it mildly. And there was another guy who was perhaps more famous than Gilbert Ling, who believed much the same. And this was Albert Szent-Györgyi. And Szent-Györgyi came from Hungary. He was one of the most creative scientists. And he moved to the U.S. He won a Nobel Prize for discovering vitamin C. And he went on to be thought of as one of the most creative scientists. Many people call him the father of modern biochemistry. And that's how important this guy was. And one of his famous quotes was, "Life is water dancing to the tune of solids." He was colorful. Water dancing to the tune of solids. So the water molecules and the solid molecules were doing a tango between the two of them. And the work that we've done more or less confirms that is the case. So it's not entirely original with us. It started with some really deep thinking of people, and Szent-Györgyi was one of them, and Gilbert Ling was another. So you might say that we stand on the shoulders of giants, but we went on to discover a lot more, and the a lot more I think has a really potentially big impact on our understanding of biology, and even understanding or development of technologies. So you asked a simple question, and I gave you a long answer. Hope that's
why we're here. It's great. So just so everybody that never heard of this fourth phase water, can you explain it? Because you already touched on some parts of what it is, but can you just summarize the most important aspects of this fourth phase water again?
Sure. Okay, so what happens is when water molecules encounter certain kinds of solid surfaces, they undergo radical transformation. And these surfaces are hydrophilic surfaces. Big word, but what it means is water-loving, hydrophilic. as opposed to hydrophobic surfaces like Teflon, where if you drop a droplet of water, it remains a droplet. That's hydrophobic. Fear surfaces that fear the water, so they don't really interact with it. Hydrophilic means loving of water, which means the surface loves the water, so the water spreads out over the surface. So we found that in general, it's the hydrophilic surfaces that create the change in water. So you can imagine the first layer of molecules meets the surface, and that first layer undergoes a radical transformation. The transformation is from liquid water to this fourth phase water, and then it's a sheet-like structure, and then the sheet acts as a template for the growth of the next layer of this fourth phase water, and the next one, and the next one. We call it fourth phase because it's a phase that is remarkably different in every way from ordinary water. We also call it exclusion zone. That was an early moniker, and it was suggested by an Australian colleague. We were telling him about this finding, and he said, "Well, you ought to give it a name because you got a name, and I could refer to you as as a woman with a pleasant smile and nice face with rose-colored glasses and dark hair, etc." But Leia is easier. So we call this exclusion zone. What is exclusion zone? Well, as these layers build, they exclude pretty much everything. It's almost like ice. In that the molecules are so closely packed that everything gets expelled as this zone builds. These layers, and so we've referred to it as exclusion zone. And in the U.S., it works very well because exclusion zone is EZ. In Italy, I think it's EZ, not EC, and so.
Yes.
We think of easy water as easy to remember, but it doesn't work so well in Europe or other places. So we think of easy. We used to call it easy water. We still do because it's easy,
Yes.
So easy to deal with. But I think the name fourth phase water makes more sense because it is essentially a different phase. Everything that we measured, everything about it is different. Okay, so you asked me to tell you about EZ, or fourth phase water. So I explained to you how it grows layer by layer. And one of the surprises was that not neutral. So ordinary water is neutral. It has no net charge. However, the exclusion zone typically is negatively charged. So you think of something negatively charged, and then, you scratch your head and say, well, wait a second. All of this started from water, which is neutral. And if the water, if you somehow have a zone that's negatively charged, you need to have a zone that's positively charged, because where do those positive charges go? They can't just vanish, right?
No, yes, makes sense.
Yeah. Okay. So we found that you've got the solid surface. I'm trying to picture a surface here, and these layers are building one by one, and this is negatively charged, and the positive charges lie just beyond this exclusion zone, or fourth phase region. So we got a negative region next to a positive region, right? And that's a battery.
Right.
And that battery has energy, like all batteries, and so you can think that this energy that is involved in the fourth phase probably has some use, because nature doesn't build batteries, or doesn't build energy without using the energy. It doesn't make any sense. So a question is, well, how might this energy be used? And one way it can be used is in your cells. So this is the stuff that basically fills your cells. Your cells have potential energy. We think ordinarily the textbook tells us that the energy comes from the high energy phosphate bond of ATP.
That's the basic
molecule.
And explanation that you get. Yes.
Yeah, that's what we're taught, and it may well be right, but I think a lot of people don't realize that idea was challenged. Soon after it was put forth, what is it, like 80 years ago? I can't remember, maybe even more than that. An attractive idea because people want to know, where does their energy come from when you start?
Right.
Yeah.
It would be nice to be able to touch the energy, right?
Well, yeah.
So it would be really convenient, right?
Well, you just you really want to know, and in that so right after that, I think it was a year or two after, Gilbert Ling points out on his website, which still persists following his demise. It's gilbertling.org. Anybody can find it there, and he
I will link it in the description.
Yeah, okay, and he discusses this challenge. It happened soon after, and it happened by a prominent group, and the group said, "Hey, there's no such thing as a high energy phosphate bond." And the people who published it before us, they made a simple arithmetic error. They screwed up. And since then, nobody's taken up the subject, so we don't know who's right. Is it the challenger who's right, or were the original presenters of this idea right? So it may indeed be that all of our energy comes from the high energy phosphate bond at ATP, as the textbook tell us. It could be that some of the energy comes from that, and some of the energy comes from the battery that we just discussed. Or, at the extreme, it could be that, all of the energy comes from this battery. All of the energy might be electrical. This needs to be followed up because we simply don't know. But of course, it's really important. And one of the features that kind of needs to be explained is there are people who don't eat. The so-called breedarians, and that's well documented now. So I've even had people communicate with me. One time, I got a call from a dancer, and she said to me, she thought I knew something about this and about the energy and the water and such. She said, sometimes I get the feeling I don't want to eat, and she stops eating. She continues to dance every day, and you can imagine how much energy is required for the dancing, and she'll go for a month or so without any eating. Wow. And she does just fine, and then she goes back to eating again. So the question is, well, how does she get her energy? It's not for food.
No.
So
what did she do that was special or different?
What, I'm not sure what you mean. Stop eating.
Well, just stopped eating. Did she do anything else to give her energy? Like,
no,
I don't know, go with the sun or something?
Yeah, the question is, well, where does this energy come from?
Right.
And so I have to tell you about where the energy comes to build this battery that I'm talking about, because it could be that this battery is where her energy is coming from. So, to any battery, including your cell phone, it won't work unless you remember to plug it in overnight or whenever to recharge it. So batteries need energy for charging. And it's the same with the battery I'm talking about, the separation of plus and minus charge. You need energy to create that. It doesn't come from nowhere. It comes from this kind of energy. And we found, or actually it was a student in the lab, a young undergraduate student, who got the answer. We didn't know the answer. We were scratching our collective heads for several years. That's why I'm missing some hair. Trying to figure out, well, where does the energy come from? You can't plug it into a receptacle in the wall that obviously it doesn't pertain. And the student found out the answer was light. So the student was working. He was working at a laboratory bench, and sitting next to him on the right side was a lamp, one of these gooseneck lamps, you could bend and
yes.
he took the lamp and he shined it on the chamber where he was working to study the fourth phase of water. And it was astonishing. He would shine the light and the exclusion zone would get bigger by a lot. He called me in. I looked at it and I was just amazed. He had the answer, apparently, that light energy, photons, the light energy is what is building the EZ. And he could shine the light and expand the EZ by a factor of 10 times. It was really powerful.
Wow.
So of course we did real experiments after that to find out which colors or which wavelengths of light were the most significant and the most effective in building this. And we found that it was not visible light at all, nor was it UV light, ultraviolet light. It was infrared light. So infrared light is long wavelength, longer than red. And red is 800 nanometers roughly, or 700. And we found that 1,000, the best actually was 3,000 nanometers into the infrared zone. And 3,000 nanometers.
Is that actually near it? Is that already near infrared or even?
Well, it depends. The characterization of near, mid, far infrared, it varies. So I'm not sure which one. Probably mid infrared, but as I said, you look at one source of information, another source, and they give you different numbers. Okay, so, but as I began to say, that's the wavelength, 3,000 nanometers, that water absorbs the most. That's known.
Yes.
So the water absorbs in the infrared pretty much throughout, but that wavelength is profoundly absorbed. So it turns out the wavelength that is most absorbed is exactly the same wavelength that builds EZ water. Maybe it's a coincidence, but it might be more than a coincidence.
Probably.
We capitalize on the energy, and that energy is all around us. We think of mostly infrared energy as like coming from the toaster or the oven. We turn it on, and it glows a bright orange, and we feel the heat, and we say, oh, it's generating infrared energy, and that's correct. However, if you were to turn off all the lights around you so that we couldn't get an image, and your cell phone would not be able to produce an image, not enough light. If you had an infrared camera, that is a regular camera with a sensor, instead of sensitive to visible light, sensitive to infrared light, you get a beautiful image of, you, your headphones, your glasses, the light switch behind you, and the brown door. Everything would show up beautifully, and that's why it's used by the military at night to see what's going on around, because everything is generating infrared energy. So it's always there, which means you'll always have EZ water if you have hydrophilic surface and water. Some of that water will turn into EZ water, and the more infrared energy you got, the higher the buildup of that ton of water. So I've presented to you a few aspects of these water. The water is ordered. it's in sheets. One sheet builds upon another, and I didn't say, but the sheets have a hexagonal motif. Hexagons.
So like bee
Yeah.
wax kind, right?
Yes, exactly. Yeah.
Isn't that the most stable structure with the least amount of material? It's ordered that way, I think.
It might be.
I think.
I'm not aware of that, but it might be right. I mean, this honeycomb kind of structure runs throughout nature. You find it everywhere, and so it's no surprise that you see it in easy water. Actually, even ice has that kind of structure, but easy water and ice are not the same. They're actually pretty close. And I'll say parenthetically that if you want to convert water into ice, we found that the conversion is not direct. You go from liquid water to easy water and then to ice. And if you melt the ice, you go from ice to easy water to liquid water. And that transition is very important because without the transition, scientists are scratching their collective heads to figure out a lot of things that don't make sense. But with this, it makes sense. And all of this is maybe beyond our conversation, but it's well described in my latest book, which is called The Fourth Phase of Water, which has become really popular. So it's in there. It's in that book if anybody is interested or curious about that. Okay, so where were we?
So I'm really curious about the battery part. So basically, you are able to create a battery energy without having to burn anything.
Correct.
So, which would be great, right? To use anyway. Is it difficult to create this fourth phase water outside of the body?
It's trivial. Hundreds of people have created. I mean, you just take a little chamber and you put a hydrophilic surface in. Not every hydrophilic surface would, but most of them in our experience. And put in some water, and we actually add little particles because the particles get excluded from the easy water, and thereby we can see where is the easy, and it grows. And in our experience is instead of putting the particles there, or even if we do put the particles there, we take two electrodes. We place one in the negative zone, and we place one in the positive zone, and you can light an LED, for example. So lighting it really works. It comes from the energy of the environment. It's free. It's always there, and also, as long as we can get hold of some water, which is fairly abundant, that's all. That's all that's required. And we've stuck electrodes, the extension, into those respective zones, and voila, we can light. The challenge, of course, is to increase the scale of this, because the amount of energy to light an LED is trivial, but the amount of light to light New York City is not trivial. So, or even Rome. And so the necessity is scale up, and scale up is possible. We just have not invested the time and energy to do it, and we'd like to do it, but it requires funding. You can't do anything without funding. You have to pay for the people who are doing the experiments and the equipment and all that. And we're eager to do it. The company that is interested could potentially come away with amazing stuff. But first, there still are some technical issues that need to be resolved. And I think we have the capability of answering those questions, resolving those issues, but we need time and we need money. And any company that's interested could benefit hugely in the future, because if it turns out that scale up is possible, then we have an amazing source of energy, and the source of energy is obtained by tapping the energy that's already in the environment. And you don't need to deplete the earth of its mineral resources to create what's created right now, what's available right now. These are features of the environment that are already there. But just capitalize on what's already there and produce potentially plenty of electricity. So yeah, you're right on. This is something with a future, I think.
It would be amazing. Like, it would be the revolution of the century. Well, the thousand of years. Like, if we could tap this kind of energy.
Well, I think the whole idea of energy coming from water, in a sense, it is revolutionary. We never think of water as being a source of energy, except hydroelectric dams or something. But this is entirely different, and it could be used as such. We're looking around now for sources of funding that we could use to develop this, because we got a big problem. We keep using more and more electricity, and we need to create it. We need to separate positive and negative charges in some way. And from everything I've learned, this is a really wonderful way to do it, if it can be scaled up. And we don't know for sure because we haven't done it, but it looks promising.
What's the biggest, well, I don't know what's the proper word for it, but the biggest gadget that you could run at the moment? So
only
an LED, but
a laboratory scale, a few centimeters in size is what we built. We built like a dozen little chambers hooked together, and each chamber has water in it. A piece of hydrophilic polymer. We actually use something called Naphion, which produces nice exclusion zones, and glass micro electrodes. And each of these chambers is like a centimeter roughly in size, and the idea was to hook them together in series or in parallel to get more voltage or more current. And we're able to do that, and as I said, we're able to light an LED, so there's no question that it works. It does work. But there are questions of longevity, and you keep the electrodes going for a substantial length of time. It does the chamber itself, elements of the chamber, do they change over time, making it impossible to get energy after, say, a day or two? We don't know. There are kinds of technical issues that need to be addressed. I think they need to be addressed before any company would rightly invest in the practical development of these devices. But it's just a matter of time. So it's kind of a you might. It's sort of like the light bulb. Light bulb was invented more than 100 years ago. It didn't work as well as it works today, but would definitely replace the candle.
Yes.
When the light bulb was available, candles became sort of obsolete, and we may use them for emergencies or for spiritual purposes, but the light took over. And that has evolved from a primitive gadget to something now that is pretty effective in producing light. And the device that we're talking about could be similar because, this is a new concept using water as a source of electrical energy. And it might take some years before it develops into something practical, but I think it can, although there's no certainty. And we'd really like to try. So,
yes.
Yeah, in answer to your question.
Like, I'm just imagining, all kinds of things at the moment where this could lead if it was developed properly,
Oh, absolutely.
So
yeah.
So it's like, for example, let's say it was possible and it was practical and stable enough, so it would make a big part of the electrical the electrical system, how everything's connected, obsolete, because everybody could just have their little water battery at home.
Well, yes and no.
For at least a few things, maybe,
Yeah, in theory, other sources could become obsolete. There may be some disadvantages of this that we haven't yet recognized. But yeah, so it goes beyond that. I mean, I'm now talking about getting electricity, but another issue that we have addressed and address in the future is purifying water, getting rid of the junk that now is sitting in the water. So, and the idea is, without going into great detail, because I need a diagram, but let's say put in a box some water with a chance to develop easy water in that box. Part of the water will turn into easy water, or easy water exclusion zone, right? So it excludes. So it means that that the water inside that box turns into two types of water. One is easy water, which has no contaminants in it, essentially no contaminants. And the rest of the water, where all the contaminants are pushed to reside. So you have a separation. It's just like the separation that occurs with a physical filter, but here there's no physical filter. So if you were able to collect the easy water, the input is a contaminated water, and then you've got the easy water, and you collect the easy water. Essentially, it's filtered water. Because it's got to a first approximation, no contaminants. It's also good for health. We didn't discuss that, but we can if you ask me, because you need, for everything the body does, it needs easy water.
Let's continue with that one too.
Well, I will, but let me just conclude. Please ask me again, because I'll forget. I always do.
Okay.
So it means you can get contaminant-free water in this way. And we've actually developed an apparatus to a reasonable extent that is built on that central principle. And we spent some time trying to improve the throughput of that. And we achieved a fair amount. So this looks really promising. And what looks promising also is separating the salt from the water. We don't have as much experience with that, but the experience we have shows that it's apparently possible. So you imagine the salt as a contaminant. Take ocean water and call it quote, contaminated by salt. It's not really contaminated, it's part of the ocean. But we can treat the salt as a contaminant and separate it from the water. So this is another potential breakthrough. We haven't studied this as much. You take ocean water, and without any source of energy apart from energy from the environment, from the sun, everything around us. You can separate the salt from the water, and what's really useful in doing this is sunlight, because sunlight, there's plenty of infrared energy covered in the sun. Half, roughly, of the sun's energy is infrared energy. So in places where there's a shortage of drinking water, like the Middle East, for example, with plenty of sunshine, but not much drinking water.
Yes.
So if this could be developed, then essentially you can get drinking water from the ocean. Wouldn't that be interesting and exciting?
Amazing.
Yeah. Well, the bottom line is that the discovery, if you will, or uncovering the nature of easy water opens a bunch of possibilities that could revolutionize the world. We don't know if it could, but it looks promising. But it needs support in order to undertake these developments. Okay, so now you were wanted to switch gears to easy water and health and life,
Yes.
Trump like that. And, I'm happy to do that. Did you want to start with a question, or should I just launch into it?
Just launch into it. First thing that comes up is good.
Okay, you want me to launch? I'm taking off. Okay.
Rocket is started.
Okay, so how do cells work? I guess. And I spent a lot of time thinking about how cells work, and the ideas that we come up with differ radically from what you will read in the textbook. And, if you would like to take textbook information as ground truth, then ignore what I have to say. If you're the kind of person who is not necessarily satisfied with ideas that are too complicated, and you believe in Occam's razor, the simplicity of nature, then you may be open to other kinds of interpretations. And so here's what we found, and I can summarize. And this appears actually in two books. It appears principally in the book before the fourth phase of water. It's called Cells, Gels, and the Engines of Life. And that was before we actually discovered easy water. That book was intended to illustrate the ideas of Gilbert Lynn. And because he was a writer who had difficulty expressing his ideas in ways that people could understand. And I felt so compelled to present his ideas, and I wrote that book. So the first half of the book deals with so-called structured water that Gilbert Lynn was talking about, and the structure that he was talking about, which we demonstrated is not correct, but philosophically it makes sense. He was talking about water molecules stacked on one another in some regular way, kind of like soldiers standing at attention. By the way, just parenthetically, the reason, or one reason why that idea did work is that stacks of water molecules are neutral. Each water molecule is neutral, and if you stack them, you can stack them from Seattle to Rome, or from Seattle up to the moon or whatever. You'll never get negative charge. And you start with neutral elements, and you can stack them, and it will remain neutral. But we found experimentally it's not neutral, so it can't be right. It's as simple as that. So the second half of the book deals with, okay, we accept that there's some kind of water structure, and what does that mean for function? Well, if you have water structure, almost nothing can happen, because nothing can get in, nothing can penetrate, and it's like a kind of static structure. So in order for something to happen in your cells, and that's what your cells are designed to do, like your muscle cells, they contract, and your nerve cells, they conduct, and your secretory cells, they secrete. In other words, they do something, right? They have a role in the body, which means they go from a kind of quiescent, unactivated situation to activated situation. It's a transition. And what we found from a lot of evidence is that there's a similarity of the way that they work. And the similarity is that when they're not activated, take a muscle cell, for example. We actually have several decades of work on muscle cells with my former interest in muscle cells. So, and when they're relaxed, when the muscle is not contracting, and then the water is fourth phase water, we call that form of structured water, but same thing. The water is very well organized, and the proteins inside the cell, which are thought to be responsible for everything. Right now, we think they're partially responsible. They're in the extended state. So you have a protein that's like this, and it's surrounded by structured water. That doesn't do anything. It's to do something. Stimulus that occurs that changes everything. It changes the proteins from the extended state to some kind of contracted state, and it changes the water at the same time. That's the sort of Unifying. It changes the water from the structured state, which we now call easy or fourth phase state, to liquid water. And then when the contraction is over, or the secretion is finished, or the nerve is conducted, it returns back. So together, this is called a phase transition, a transition of the water and of the protein. So it's not just the protein that changes; it's the water that changes as well, and and then it returns to its initial state. And the return is the energy requiring state, because in order to convert bulk, ordinary liquid water back to structured or easy water, you need energy. You always need energy to go from randomness or from disorder to order. So that's the cycle that we found to operate at the cell in general. What cells do in order to accomplish what they're designed to do is that they undergo a transition from the ordered state with extended proteins to the disordered state, like liquid water, to contracted or shortened proteins, and then back again. So this is that's a sort of prelude to when I want to talk about. It's a prelude because you need to, or one needs to understand that this easy water, you need to have it in your cells. Otherwise, what I just described, this cycle from ordered, disordered, and back again, which is an essential feature of what we think all cells undergo in order to do what they're designed to do. Can't do it if you don't have the starting state, the easy water that's in your cells, and so your cells need to be filled with easy water, and that's the issue. Sometimes for whatever reasons, pathological or dehydration, not enough drinking of this stuff, your cells are not going to function properly. The cells will be somewhat dysfunctional. In the case of muscle, they're not going to return to the initial state where the proteins are extended and the water is in the easy state, and your muscle will remain contracted. You'll get a kind of lump. Can't go back to the relaxed state. But if you rehydrate, if you massage or whatever, eventually, the energy of your hands, eventually it can go back. So you want to make sure that your cells are absolutely filled with easy water to be functioning normally. So then what the issue boils down to is, if you want to retain your health, what do you need to do? And I would argue that what you need to do is not to go to your physician and take more drugs. Some would that, and I think in a, you might say a more natural way, you need to build the easy water. And so the question might be, well, how do you build the easy water? And there are a half dozen different expedients, simple ones that I can detail if you.
Yes.
Okay, you want me to detail? Okay, so one is drink more water. Okay.
I mean, that's simple.
Yeah, that's very simple. And what happens is that some of that water, you lose some of the water. It gets peed out, but some of the water gets converted into easy water, and then can refill your cells. And the way that happens is that you've got lots of infrared energy from outside coming to your body, and also inside because metabolism generates heat, and so the core of your body is generate heat, which is essentially equivalent, not exactly, but essentially equivalent to infrared energy. You've got infrared coming from inside and from outside, which then converts the water that comes in, which meets hydrophilic surface, and converts it into easy water. That's one way. Another way, and that's the hydration, basically, with hydration of your cells. Another way is to drink easy water itself. So then, in that case, your body doesn't need to undergo or undertake that conversion. And so some waters that you can purchase or get from springs contains water. You can do it that way, but a better way is to go to your backyard and pull the leaves from freshly grown plants, crush the leaves to squeeze out the liquid. So what's that liquid? Well, that liquid is the interior of the plant cells, and we found that as you might expect, animal cells contain lots of easy water, and plant cells, and since they're freshly grown, they have a full complement of easy water. So you squeeze out the water. You don't want to fill yourself with the whole plant because it's just, then you stop drinking. But if you take the juice and if you supplement the juice with something good tasting, so that to make it more palatable, it works. And I've been told by a fair number of health providers that that's the first thing they suggest. Someone comes with some either weird symptoms or not so weird symptoms, and the provider many providers will say, well, do what I just described, and they come back a few months later and they feel better. It almost doesn't matter what the issue was. They come back feeling better, and also they seem to lose weight. I don't know why, but as a result. So point number 2 is drink easy water. Go ahead.
I have one more question to that. Does the easy water get destroyed through cooking?
Well, that's a really good question, and I have to think about the answer to that question. It's a funny thing that you asked, because we're going to have a symposium on issues just like that, the role of water in cooking, and then my job is to invite a half dozen scientists, and the chef on the other side is a 3-star Michelin chef who lives in Provence, and we're going to get together. He's going to invite a half dozen of the world's most famous chefs. We're going to get together and discuss those issues, because this guy, his name is Heston Blumenthal, and he runs the restaurant called the Fat Duck, which is near Heathrow Airport, and was once voted to be, quote, the best restaurant in the world.
Oh, wow.
I don't know who voted or how, but it had that distinction. So Heston and I are going to be running the show, and it'll be interesting to find out. Offhand, here's what I'd say, and maybe it's premature, but when you heat something, you're adding infrared energy. So if you already have EZ and you put in infrared energy, you can have more EZ in theory. And so that might happen. And if that's true, you can then explain why people have this common experience. You make stew, and it tastes pretty good, especially if you're a 3-star Michelin chef. It'd be pretty good, probably. But if you reheat it the next day, you're adding heat. You're adding more easy water, and easy water is the site of storage of information. We haven't talked about information in water, but presumably that's where the information lies, because it's an ordered, regular array, just like the ordered array in a computer memory, and it also, you have hydrogen and oxygens, and it turns out the oxygens can have different states, just like computer memory. A transistor will have like a 0 or 1, and the oxygens can actually take on 5 different states. This is standard chemistry. We call it sometimes valence, -2. There's also -1, 0, +1, +2. So it's another entirely different topic, that EZ has a capacity for memory or information storage, and there's by now a huge amount of evidence for information in water, and that you might or might not know about it, but each year we organize the annual conference on the physics, chemistry, and biology of water, and I invite people who believe they have evidence for water memory, a controversial topic for sure, but I know that there's a lot of evidence for water memory. So yeah, when you say, to your original question, what happens when you heat? I can, there may be more to it. There probably is, but I can simply say that we know heat, infrared energy, builds easy water. If easy water is the site of storage of information, which we mean flavor, to get more flavor, you build easy, and you can do that by heating. And that may be why stews and other foods can taste better when reheated second day than on the first day. There's a more of a volume of flavor. I hope.
I want to tell you my thoughts about what you just told me. So I'm trying to think as you tell me to think.
Okay.
So could it be that the cooking or the heating up of the stew is kind of like so maybe the first time it gets like disorganized through the cooking, because the food was used to, let's say, the input from the sun, which is very regular, right? So then the heat from the stuff, let's say, is a different.
The heat from the
from the stove, from the cooking, is a different pattern. So it disrupts the original one, and then with the second, it kind of brings back regularity, because it's the same kind of input, which is kind of like a rhythm. Does that make sense?
Well, yeah. I mean, that's certainly a possibility. I think it needs to be studied.
Well, that's a good answer.
Yeah, the answer is not clear. Also, okay, let's go on to the next topic, because we're maybe getting off track. Please. What
was the next one? We were talking about health and easy.
Oh yeah. Okay. So I went through a couple of expedients. Another way is to expose yourself to the energy that builds easy water, and that would be, for example, to go out in the sun. You know that going out in the sunlight can be health. It can induce health, but the reasons are a little bit vague. In Seattle, where I live, in the wintertime, today's an exception. The skies are usually gray, and we have a lot of rain. Not heavy rain, but the weather is a bit like London, and about a gray skies. And once in a while, like today, the clouds will part and the sun will peep through, and people are smiling and they're feeling good. So why? Well, your first thought is, it's psychological, and that is certainly possible. Another idea is that the sun is reaching your brain. Sunlight and infrared energy is known to penetrate even your skull, because you can actually image the brain by starting out here with infrared energy. Infrared goes through the light. Infrared light gets scattered by your brain, is then collected again outside to penetrate your skull again, and you can get an image of the brain. Obviously, you can get an image. The energy must go this way and then come back out again, so it does pass through your skull. And if the infrared energy passes through your skull, it's going to build easy water in the cells of your brain. And then the brain is going to function back to normal. What's normal? Well, I think normal is feeling good, not feeling depressed. And it'll do that. So so that's exposing yourself to the sun is a good idea. Now, another way that's more powerful is exposing yourself to a sauna, or as the Finns say, sauna. What does that do? Well, you take off your clothes, you're sitting in heat. And heat is essentially the same as infrared. Infrared energy is penetrating your body, all over your body. It builds easy water. That's confirmed in the laboratory. And in building easy water, it returns you to health, to the default condition. And if you start with a headache, you may wind up without a headache. And if you start with a pain in your knee, you may wind up without a pain in your knee, et cetera, because proper function depends on the presence of a full complement of easy water. And that heat, whether moist or dry, is powerful in generating easy. So there you go. So those are two more. That's 4 so far, and I've got number 5 and number 6. What are 5 and 6? Actually, there were more. What's number 5? Let me think. Oh yeah, number 5 is or many people know that there's certain herbs and such that seem to be good for health, and these herbs, or the knowledge that they're good for health, derives from thousands of years ago. For example, the Ayurvedic culture in India, the ancient Chinese culture. And the people who lived then were maybe just as interested in preserving their health as we are. They didn't have the drug companies. You can argue whether that's fortunate or unfortunate. So what did they do? They found out that certain herbs are good for health. And today there seems to be a revival in that. And, in scratching our collective heads and trying to figure out what's going on there, one thought arose. So take, for example, turmeric. Everybody seems to be into turmeric. And the Ayurvedic culture, people knew that we had a problem. Turmeric was usually good, and so we're trying to think, scratching our heads. There are two possible interpretation that we could think of. One is that inside your body, all over in each and every organ, you've got a turmeric receptor. And if you take turmeric and hits the receptor, something happens which confers good health. That's a complicated hypothesis. A simpler hypothesis is that turmeric impacts the water, and the water then is everywhere, so it doesn't matter whether it's your eyeball or your rear end that's got a problem, it's going to get there. And so we tested experimentally if we have a setup in which we can see easy water, and the question is, if you add a little bit of turmeric, does the easy get bigger? And absolutely it does.
Oh, really? Wow.
Yeah, and it's not only turmeric, but we investigated now more than a half dozen different substances that are known to confer good health. So it includes basil, holy basil, the two. We looked at ghee, clarified butter, and all of them, and several additional ones. They all built easy. They grew easy, and so it, at least one hypothesis for the reason why these substances build health is they build EZ. We can restore the full amount of EZ in cells that don't have the full complement of EZ. We also tried a poison, thinking that, well, we have now a hypothesis that these substances that are good for health build EZ water, and so you'd expect that substances that are not good for health, like poisons, diminish the amount of EZ water.
Makes sense.
So we tried glyphosate, and well, in Italy you have this, but we have this chemical called Roundup, and it's basically glyphosate, and it kills weeds. So you have other plants that are genetically modified to be insensitive to the impact of glyphosate, Roundup, and then the corn or whatever, it grows very nicely without competition from the weeds. The only problem is that, according to the evidence, it's not without impact on us. You could think, well, it kills weeds, but it doesn't harm us at all. But the evidence is opposite. And in case anybody's interested, the person who's collected all the evidence is Stephanie Seneff from MIT. And she spent many years collecting, and she's very effective at doing that. And so if you look at her, website, you can find the evidence for that. So anyway, that poison did the opposite. So we're pretty confident now that the reason why these substances, long known, thousands of years for promoting health, do promote health, and the reason is they build EZ water. Okay, so that's number 5. Put turmeric in your diet. You should be better health. And number 6 is connecting yourself to the earth electrically. So you know about it, but other people may know less about it. Why does earthing, or we say grounding, why should that confer good health? Apparently it does, and there are actually commercial devices available. You can, for example, put your bare feet on a sheet of aluminum that you can connect electrically, and connect it to an iron rod that's driven into the earth. And my son, who does the illustrations for my books, does that and feels better. And a lot of people feel really good. You can have the same effect by walking on wet grass without your shoes, or walking right on the beach near the ocean where the sand is wet. And you're connecting yourself electrically to the earth. So why should connecting yourself electrically to the earth make a difference at all? Well, there are lots of theories, and of course we have our own theory, and the reason is that the earth is not neutral. The earth has a net negative charge. When I first heard this from a Russian colleague, I couldn't believe it because I started my career studying electrical engineering, and no professor ever told me that the Earth was anything but neutral. So you plug in a plug with 3 prongs, and the third prong is supposed to connect to the Earth, and it's connecting not to neutrality, but to net negative charge. And there's lots of evidence for it. It's just that we never learn about that. It has seemed almost irrelevant, but the evidence is ample. So now, why does connecting yourself to the negative Earth, what does that do for us? Well, we found if we take a beaker of water and we stick 2 electrodes in, and we pass current, and we look around the negative electrode, we see easy water building. So the mere passage of electrons from the wire to the water builds easy water. So if you connect yourself to that source of negative charge, you can build easy water. And so that's you might say the 6th mechanism by which you can confer health. There are more, but I think you've got enough for now. Maybe we'll go to ask some other questions.
If you still are okay with the time,
I got a few more minutes.
Okay. So just a short. No, because I wanted to ask something, but it will probably be a long one. So, because the memory part is also really interesting of water. So I'll tell you a little bit about my relationship with water lately. So, because I'm not the biggest thinker about it, but I listen to my body. So it has been really interesting to implement different kinds of strategies to change the water. So, for example, we have relatively good tap water here, but it is it's still, you can still make it better, right? So, for example, I put it outside overnight and it will taste better the next day. And I will be able to drink more and have thirst for more compared to just drinking it straight from the tap. So, and I've noticed also there's differences in the taste from summer and winter, and the best one is on a snowy day. So,
you mean melted snow? Is that what you mean?
No. If it's snowing at night, the water will taste the best the next morning. It won't snow into the jug. Just,
okay.
I guess, the information that's around. It's just something I noticed recently because it has been snowing. So, yeah.
Oh, well, what's going on? Well, it's the first time I've heard that, and
yeah.
Well, so first of all, I could imagine that tasting, if you taste water that contains a lot of easy water, it'll taste different from water that doesn't. And you can lay out an array of waters and taste them, and they will taste somewhat different. Meaning that something really is different because your taste is pretty sensitive. No, it's a good question. Makes me scratch my proverbial head, or head. Well, I guess the simple answer is I don't know. I don't know how to explain that, except, of course, if you're tasting easy water, if you're tasting bulk water, they're going to taste different because they're completely different species. And often there'll be a little bit of easy water in any source of water that you drink. The more the easy water content is, the healthier the water will be. And so if you've exposed water to charge, I was just talking about, you get a negative charge, you get easy water. And I'm just wondering, these are closed containers that are exposed to the snow? Is that...
It's a jar, like a jug that's open.
Oh,
kind of
so
like
the snow is falling into it.
No, because it's like there's no snow that's falling into it. But I put it outside of the house, in front of the porch, on the stairs.
Okay.
And it's not covered, so there can be direct light and dirt also. But usually not, because it's open, and it's a glass container, and it's like a brown jug. And what else? Yes. I've also put it directly in the garden, so on the grass, but it's just far away, so it's inconvenient. So I just put it outside of the porch usually.
I guess I gotta say, I don't know the answer to that. However, I can speculate. So,
Sure.
one of the features of, shall we say, rainfall, and I guess maybe snowfall, is going to be similar. Although I hadn't thought a lot about snowfall. There are electrical features. So when it rains, rainfall is not simply the unzipping of clouds, allowing the droplets to come and fall. And the reason that's known right now, although not widely discussed, is if the raindrops are simply falling, you can calculate the velocity based on the size of the droplets. For example, if you were to or not you, but maybe someone else, jump off the top of a tall building, you'd start accelerating, and then you reach a terminal velocity, and it won't go any faster than that. You'll stay at that velocity.
Right.
Maybe that's somewhat reassuring, but you still probably won't make it if you jump from a tall building. So at any rate, people who studied rainfall about years ago was a paper, and they found that speed of descent was higher, up to 10 times higher than the so-called free fall velocity. And they concluded that somebody's pulling the raindrops down. So that's rainfall. And by the way, all of this is discussed in my forthcoming book, which I hope will be out in the next 6 months. The limiting factor is my artist son, who has been busy remodeling his home. So there's been a 3-year break, and now he's back to finishing the artwork. And I hope the artwork floats. Indeed, it's finishing now, and he's transitioning to working on finishing the artwork, which means maybe 6 months or so. And I spent 4 chapters on weather. We don't understand weather at all. We do people are doing computer models to figure out when it rains, it doesn't rain, but there's no physics that begins from the fundamentals and builds up to hurricanes and tornadoes. And I attempted to do that in the book. And I discuss a really important phenomenon about rain. And I introduce it by saying that the raindrops fall really fast. They're pulled to the earth. Why are they pulled? Well, I think the reason has to do with electrical charge. And I'm coming to answer your original question about the taste of when it's snowing, the taste of the water. And So what happens is that if you have, do you know about Faraday induction or induction of charge? Okay, I see a negative response. This is one of the factors or one of the formulations in physics that to me makes a lot of sense because it's so simple. So if you have a charge sitting here and the surface sitting here, let's say there's a positive charge. What it's going to do is induce negative charge on the surface below. It takes all the charges and pulls the negatives to the top. We got a positive charge here, it wants to attract those negatives. It pulls them to the tops, and it pushes the positive charges down to the bottom. Where exactly you're cut off, I was talking about induction as being relevant to your question and to clouds. So if you have a positive charge here, it induces negative charge at the top of the surface. It's called Faraday induction. And so you have positive here, negative here. They attract each other, and they come closer and closer. So in the case of a cloud, the same thing happens. It's up here. Clouds have negative charge. This is known. They'll induce positive charge here. That's confirmed. And as we get closer, the cloud will begin to descend, and the effect becomes stronger and stronger as we get closer and closer. So the cloud is going to induce the opposite charge on the surface. Now, if you've got some water that's sitting at the surface, it's going to have an impact on that water. And the impact of water is to induce opposite charge at the top, and maybe negative charge at the bottom. And so when you drink that, it's going to have an impact on the flavor. I don't know if that's the reason why you experience what you experience, but I guess that's where I'd start as one hypothesis to explain it. Needs more thought, but it's a possibility.
That's really interesting because I don't know how to explain those things.
Well, I don't know how to explain them either. This is a speculation based on what I know. Whether speculation is accurate or not, I'm not sure.
Maybe we'll find out one day.
Yeah, we may find out. But the bottles of water, especially colored bottles of water, were also used during Ayurvedic times. And there's somebody working in my laboratory who comes from India, and she said her grandfather used to put out jars of water, and each jar had a different color, be filled with water and capped. And when she was ill, grandfather would say, "Oh yeah, you got this such and such illness, drink the green one or drink the red one." And apparently it was effective. And so I could imagine that, if you painted a certain color, certain wavelengths will get through and other wavelengths will not get through, and it could impact the water, because we know that light affects the water, different wavelengths in different ways. So, this is a phenomenon that's you won't find in textbooks, but from common experience dating back 5,000 years, it may be true. And I think, progressively we're coming to realize that the ancients had a kind of wisdom that we practically reflexively reject, but they knew a lot more than we give them credit for.
Yes.
Especially the Italians.
Other places too.
Other places too, but Italy for me is one of my favorite places. The Italian people, the Italian food, the welcoming demeanor of the Italian people, and the natural beauty. When you put them all together, it's a favorite place of so many people I know. So congratulations for living that.
Well, thank you for saying it. Yes. I forget sometimes because I'm sure all the time.
Yeah, I know. It's like having a wife or a husband. at first you appreciate their virtues and such, and after a while it becomes so normal that you forget. Yeah. So there we are. Have I answered your questions adequately?
Yes, this was extremely interesting. I'm super happy we could talk.
Okay, thank you. Now, you told me earlier that I had to hang on because to make sure that everything is uploaded or whatever. Please tell me what I should do.
Yes, so to close off, you can tell the audience about your laboratory and other things you're involved in, maybe social medias, so that they can maybe
sure.
know more about it.
Social media, not very much. We have a Facebook page, but that's about it. I don't have the time really to deal much in the way of social media. But I would like to say that when I have time, it's devoted to thinking and writing. And I've got 2 books coming. The first I should say about the 2 previous books. The first is Cells, Gels, and the Energies of Light, which you'll find has mixed reviews because a few of the reviews say, oh, this is about Gilbertling, and we know he's a crackpot, so pay no attention to it. And the flip side, there's a review by a Harvard cell biologist, and, he's from Harvard, you got to take him seriously. He said this is a 304-page preface to the future of cell biology. I like that.
Whoa.
Better. So mixed reviews. Nevertheless, obviously, I think the material is important and relevant. And then the 4th phase of water, that has, I don't know what adjective to use, but the reviews have been amazing. So many people are interested, and there are translations in now I think 9 languages, and increasing. And I encourage anybody to just take a look at the reviews. And sometimes if I'm feeling a little bit depressed, which is not often, I take a look at the reviews. I feel good. They're amazing. So, okay, and then two new books are coming out. And by the way, there is an Italian translation of the 4th phase of water for people who prefer Italian, but if they read English, the original is always the preferred one. So 2 books are on the threshold as soon as my son gets his act together, my son, the artist. And one of them, the title, I can't remember the exact title, but it starts with charged in big letters, and then blah, 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 at the bottom. And it deals with the role of charge in nature. So throughout nature, we have a primitive understanding of a lot of different phenomena. And sometimes when you try to scratch beneath the surface, you discover that the current interpretations don't make sense. We can't go anywhere with them. For example, you take gravitation, which is actually treated in the book. It's one of the 10% or 15% of the book. It's really easy. If someone, a middle school student asked you, what's gravitation all about? Why are we stuck to the surface of the Earth? And your response is probably, well, masses attract. Bigger masses attract more than smaller masses, and so it depends on the mass. And then you go beneath the surface and you ask the question, why do masses attract? You're stuck. You don't know the answer. And when you get stuck like that, when you go slightly beneath the superficial explanation, you can't say, well, they attract just because they do to something. It's unsatisfying. When you have a situation like that, you have to ask whether the current explanation for that was correct. And that is one of the areas I deal with. Another one is what turns the Earth every 24 hours. What's weather all about? Why does wind blow? And, these are questions that either you'd shrug your shoulders and say, I don't know. Or you'd come up with some rather superficial explanation which you have trouble defending. And so those are some of the subjects that I deal with. Another in the book, how do birds fly? Well, if a middle school student asked you, or a younger, you'd say, well, they flap their wings.
Right.
But they don't always.
It's not the first.
And, yeah. So there's something else that's going on. Some birds, like I see eagles flying from, there's a tree, there's a nest right in opposite my house, and they fly pretty much every day, and they may flap their wings on occasion, but mostly they don't. And they can fly level, or going up, or going down, without flapping their wings, and they can fly into the wind, against the wind, at the right angles to the wind, and they seem to do it no problem without flapping their wings. So it's necessary to explain how that happens. And in the book, I explain it. And many of these phenomena that I'm talking about are resolved if you invoke electrical charge. And, obviously, I can't describe here and without diagrams and whatever, but I think that electrical charge is far more fundamental for all aspects of nature, and we get charged for credit for it. And finally, the book that will come right after that, it's essentially done, deals with the structure of the atom. Now, all of us have learned that the atom is like the solar system. It's got a nucleus that's positive, and it's got electrons around it that are negatively charged, or electron clouds. And we kind of don't think of the fact that model is inadequate. Added to that model have been the subnuclear particles, which number, I think, 60 or more than 60. And those are necessary components for the model to fit observation. And when you have a theory that requires the continual addition of new aspects, new things, you have to kind of scratch your head and say, I'm a little skeptical, because a good theory actually explains even more than you expect at the beginning, without the addition of extra parts, particles, whatever, to it. But there are some objections that are so simple. For example, the nucleus contains protons and neutrons. The neutrons are neutral. The protons are positively charged. Therefore, they repel one another. And if the parts of the nucleus repel each other, the nucleus should explode, right? The positive charges want to get as far away as possible from other positive charges, simple with electrostatics. And so the physicists came to realize that early on, maybe close to 100 years ago. In order to deal with that obvious problem, they invented something called, quote, the strong force. The strong force is like a glue that holds the nucleus together. It's sort of like a Band-Aid covering a gaping wound. I've never seen any independent evidence for the existence of a strong force. It's something that's invented to solve an obvious problem. But it's not the only problem. We think about the positive nucleus and the negative electrons, right? And what you learned, I learned, is that plus and minus attract one another. So how come the electrons don't collapse onto the nucleus and the atom will vanish into a point?
Right.
I think you never thought about that.
No, I never thought about that.
Something that, and so you can either invent maybe another kind of force that keeps the electrons away, but it's not a satisfying solution to the problem. Another possible solution to the problem is that the model is wrong, and that we need to look elsewhere for a model of the atom. And that's what I do in the book. I do that, and I demonstrate that there's an alternative approach that explains things in a more satisfying way. And it turns out that that approach it's not so different from the approach that was taken by the dominant chemists of the day. See, the chemists didn't like this solar system model. They said, or the most prominent chemists, that was Irving Langmuir and G.N. Lewis, names that we know today. And they said, this model, the solar system model, doesn't explain even the simplest of chemical reactions. They didn't like it. But the chemists were not dominant that day, or that era. It was an era of the physicists. And so when the physicists came out with this or Niels Bohr, with the solar system model, the physicists all embraced it, and the physicists were dominant, so it got in the textbooks, and it persists to this day. And most of us think, well, since it's been in the textbooks for 5 generations or 6 generations, it must be correct. But you got to remember that early on the chemists said, no way. And one of those chemists came up with his own model, and it's illustrated in the notes, which I'm reproducing in my book. And the model they came up with, I just recently found out, is very similar to what I'm suggesting, which gives me some confidence. So anyway, I'm sorry I've taken a long time to describe 4 books, 2 of which are out. I'll let them. Anybody interested in the subject might like to take a look. And 2 books that are coming. The first, I hope, in 6 months or so, and the second within 6 or 8 months after that. And so maybe I will end there.
Yes.
There are many more things going on, but they be too much blah blah blah.
No, it's great. I found it really interesting, and I will also link the books that are out in the description below, so people can go directly there and soon self-going purchase.
Amazon
if you want to.
is the usual place. It seems that all books seem to be sold by Amazon these days.
Yes.
Okay.
Thank you
So
so
anyway,
much.
it was a pleasure. I'm glad we connected, and I hope some of the information was useful.
Yes. Thank you so much for coming on and spending this time with me.
Okay.